Okay, welcome back. CP 517-WS, Digital and Computer System Architecture. This is the last part of lecture 2, part 6, Power, Energy, and Dependability. I'm your Professor Hang Liu. Power and energy. The problem definition is that how much power you put to get it in, how much power you get it in, what you consume requires that much power to remove those heat that generated. Okay, so this is actually a very important problem. And it's, I think, a big problem from 2004, end of denial scaling, that moment. So thermal design power characterized is sustained power consumption used as target for power supply and cooling system, lower than peak power, higher than average power. Clock rate can be reduced dynamically to limit power consumption. Energy per task is often a better measurement. Define and quantify power. So there are two types of power. First is dynamic power, second is static power. So first, let's see what is dynamic power. Okay. So for CMOS chips, traditional dominant energy consumption has been the switching transistors, that is dynamic power. So for dynamic power, the power consumption equals 1/2 multiply capacitive load multiply voltage square multiplies frequency switched, right? And then the average energy consumption, because the energy is the time multiply power, right? So it's different. Okay, this is very important. You basically get rid of the frequency switched because the frequency multiplied the 1 frequency is the time. For mobile devices, energy is a better metric, but for CPU, probably power is a better metric. For fixed task, slowing clock rate switched frequency switched reduces power, but does not affect energy, right? Capacitive load function is a function of number of transistors connected to output and technology, which defines capacitance of the wires and transistors. Dropping voltage helps dynamic power and energy. That's very important. And the help is not just linear, it's a square, right? To save energy and dynamic power, most CPUs turns off the clock of inactive modules, like a floating point. Okay, can you use 15 minutes to say if we reduce the 15% of the voltage and the 15% of the frequency, what's the impact of the dynamic power? Use 5 minutes. Please pause this video and do the work. Okay, this is the result, right? Reducing power, the techniques to reduce power is voltage scaling, right? DVFS. I believe everybody remember this is the second thing. Lower power state for DRAM and the disks. Overclocking, turn off the cores like dark silicon. Static power is the leakage of the power. So even when you turn off the transistor, you still have a static power. Static power is proportional to the static current multiplied the voltage. And actually, according to some study in 2006, the power leakage is 25% of the total power. Right. So even gate voltage to inactive modules to control loss due to leakage, like a power gating, right? Okay, that's power, and second is dependability. Power and energy, and then dependability. Dependability is very important. How to decide when a system is operating properly? This is actually very important. I think a couple of days ago, Google has been out of service for 5 minutes or so. And people said that lose billions of dollars, okay? And then Amazon data center in Ashburn, sometimes also, I think in 2008, they have a human-based failure because the data center manager deleted some lines of the bash, and then that causes the entire data center down for a couple of hours. That's the revenue loss of billion dollars because a lot of companies rely on that to do that service. Or you can just imagine if you have your network company being down for like half a day, that essentially costs you half a day of your work, right? So we see this is called service level agreement to guarantee that the network and power service would be dependable. Service accomplishment, where the service is delivered as specified. Service interruption, when the delivered service is different from the SLA. Failure is transition from state 1 to state 2. Restoration is transition from state 2 to state 1. Some taxonomy, okay? Then we have these kind of very important terminologies like module reliability, the measure of continuous service accomplishment, or time to failure. Or mean time to failure is the mean TTF, right? So measure the reliability. Failure in time, or FIT, is the rate of failures traditionally reported as failures per billion hours of operation. Mean time to repair measures the service interruption, like between how long you have to repair this interruption. Mean time between failure equals the mean time to failure plus mean time to repair, right? Module reliability availability is the mean time to failure, which means the available time over the total time, the mean time to failure plus the mean time to repair. So we want the module availability to be 99.999, right? This is the availability. So 5 lines, 4 lines, 3 lines. This is some very typical word you use when you are talking to your data center provider. Okay, can you guys use 15 minutes to do this calculation? If modules have exponentially distributed lifetime, overall failure rate is the sum of the failure rate. Calculate the FIT and MTTF for 10 disks. Okay. Okay, so once you finish this, then we come to the conclusion. So for today's this lecture 2, we track and explore latent technology part of architecture responsibility. We deal with benchmarks, right? We talk about power, energy, and dependability, right? So the homework of this lecture would be exercise 1.16 in the textbook. For the due time, I'm gonna update in the Canvas. Please don't use this due time, okay? Okay. So for due time, please the Canvas, okay? And then please read chapter 1, Appendix A and Appendix C for next class. All right, see you.